Hey everybody, we're 3 out of 8 videos through on day 8. I have a set of remaining videos for you about various representations of sets in Coq. We're going to look at 3 representations, 2 used lists, one a very simple representation that we'll talk about now, one a more advanced one, and then another one where we'll talk about how you use binary search trees from day 7, how you use those to implement sets, a very common application of binary search trees. So I'm going to skip over some text right here. That is the sort of like textbook discussion of what we see in the first 3 videos that I made. I think it's really worth looking at. It's slightly different content. It's slightly different ways of expressing similar ideas. If you're confused, reading this might help. I think if you read this and you're confused, watching the videos will help. Maybe bounce back and forth and take any questions you have to Zulip. So let's get started. Let's look at our simplest implementation of sets, working with them just as lists. So we're going to say a natset, a set of naturals, is a list of naturals. So throughout this file, we're only going to talk about sets of naturals. Of course, you can have sets of other things. And in fact, in the videos, I show sets of heterogeneous types, right? Sets that contain booleans and rock, paper, scissors, or booleans and numbers. We're only in Coq going to talk about homogeneous sets, sets containing things of the same type. The way we're going to start is the way natset's going to work. It's a list of naturals, and we're going to maintain the invariant, like we've already seen, invariant for the search property. We're going to maintain the invariant that we don't have any duplicates, right? That's what we want. So let's define the operations that maintain this invariant and give us a good representation of sets, knowing we're going to have to be careful because under the hood, a natset for us is just going to be a list of naturals, so someone could write some bad ones. So in our representation, here's 2 different ways of expressing the even numbers up to and including 10. Now, we're going to want to consider these 2 sets equal, even though they have different representations in the computer. You'll notice the order matters to the computer, but it's not going to matter when we're talking about what actually constitutes a set. So, okay, there's some thinking to do there. These are both good natsets. They're both going to sort of meet our invariant. This next one, the non-set list, this is a bad natset, right? I wrote the type list nat, but I want to note for you that if I type natset here, Coq accepts it, right? Nothing about the type natset is going to forbid this. We just have to be really careful. Now, you might wonder, why is this bad? Well, the number 2 appears twice, and sets are supposed to be just holding distinct elements. So our invariant for these early natsets, our first attempt, is just going to be no duplicates. That's the rule. So natset, yikes, has type natset, not a good look. All right, so we've already seen this problem. Let me get rid of those line numbers on the side. We've already seen this problem for binary search trees. So the answer is, again, just kind of be careful, define your operations correctly. Okay, so in the next video, I'll be defining the natset operations. And then after that, I'll have 2 videos about a different way of talking about sets of naturals, representing them as lists, a different invariant we could have that has pros and cons. After that, we'll have the video on BSTs, and that'll be it for today. Okay, talk to y'all soon.